Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. The series we're in is Cost-Benefit Analysis, and this is the third installment in the series. The first installment was just kind of giving the basic model and assumptions. The second was talking about the first order approach. And in this installment, I'm going to say a little bit more about the first order approach, but mainly I'm going to be thinking about fixed costs and let's call it the entry decision. Okay, so does the decision maker even want to choose any scale at all? Maybe they just don't want to do it, period. So we'll get to that. Let me go back. Thinking about the first order approach, I want to just do one more application that is just sort of shows the flexibility of the cost benefit approach. And it's you might not think of it in terms of that, but when you see it, you realize, okay, yeah, we can use these techniques and we can solve that. So So what I want to do is I want to think about an agency, or maybe you can call this decision maker a social planner, that has to choose the scale of some project that generates public goods to some group of people. You can think of it as a society, or maybe it's people who live in a town, or just anything that benefits some group. Okay, so I'm going to have n group members. And there's going to be this non-negative scale of some project. Okay. But I don't want to just write down a benefit and cost function. Okay, so I want to think about a problem with more structure that's kind of interesting, I think. So, so this decision maker or planner has to choose a project scale, but that has to, you can't just snap your fingers and it appears. That has to come from somewhere. And so I want to think about a situation where each member of this group has some income level. Okay, obviously they decide how much they're going to work, and but I'm going to not model that part and just say, okay, they have some income, and where, how is this project funded? It's going to be funded through some proportional tax. Okay, call the tax rate T, and we'll assume that this has to be between 0 and 1. Okay, now we're going to assume that members of this group, they get some benefits from this project, but they don't want to just give away all of their income for this, because they also get benefits from private consumption. Okay, and we'll call that YI. YI's individual I's private consumption. All right, so just given the structure that we put on this, you can, certain connections arise naturally here. So we'll assume that let's assume that, so X, this project scale, will just be generated from taxation on all these individuals. So if you're individual I with income I, and the tax rate is T, that means that you're contributing this amount of money, T times your income, toward this project. and each person's doing that. So the total contributed to the project is just the sum of those across the n members of this group. Okay. Person I also gets to enjoy some private consumption. We're not going to have savings in this model. So basically, anything that is not taxed away, the individual will use that for consumption. Okay, and here we could have prices of consumption, and you know, we could put in other parameters, but this will just keep it kind of clean. Now, what I want to do is I want to think about this social planner or decision maker who is choosing this project scale to maximize the sum of welfare of all the members of this group, and the planner has to have some way of measuring that, and the way the planner will measure that is as follows. Each individual is going to, you know, get some benefits from this project scale, and we'll raise that to this power beta. And then we'll have, or actually, do I want to use alpha? No, I'll use beta. All right. And then from consumption, that's just going to be a linear term. All right. So that's how our planner is going to measure the welfare of each individual. You can think of this as a utility function, but in fact, that might not be the best way to think about it, because the planner's problem is to maximize the sum of those. All right, so the planner is going to maximize the sum of each person's benefit across this group. Okay, so it doesn't really make sense to add up people's utilities, at least if you're using utilities in the ordinal sense. Then it really doesn't make any sense, because you can, you know, as we've talked about in a different series, but if you have an ordinal utility representation for a decision maker, you can, you know, take any monotonic transformation of that, you can multiply it by 1,000, it still is a utility representation. And so, you know, if you're adding up people's utilities, it's kind of weird, because then you would actually have to choose one utility representation. You can think of that here as what's going on, but I just tend to think of it as more the social planner is just going to measure person I's welfare in this way, and then is going to maximize the sum of the individual welfare. Okay, so well, this maximization problem is a little funny. I'm not saying what we're maximizing with respect to, but let's use some of the structure we've imposed. So we know that the and actually I'm going to be, well, let me write this first. Okay, so X is this the sum of individual contributions. Because the tax rate's the same for each person, right? That T there doesn't depend on the person, on the member of the group. We can pull that out of the summation. Okay, and write it like so. But now let me just simplify notation a little bit, and I'm going to use capital I with no subscript to denote the sum, the total income of the group. So capital I is just the sum over individual income. All right. Now, so where were we? So if the planner wants to maximize the sum of x raised to the beta, well, we know what x is. It's the tax rate times the total income of the group. And remember, yi is just this income person I times 1 minus the tax rate. Okay, so that's the planner's problem. And because of the structure, we're able to see that, well, okay, so the project scale, the individual private consumption, that's all determined by a tax rate T. And so we can think about the planner as just maximizing with respect to the tax rate. Okay. All right. So what does this have to do with cost benefit analysis? Well, let me rewrite this. First, though, I see that I have a problem. This should be a plus here. Okay, and that's a plus. All right. And anyway, so I'm going to rewrite this objective function. The first part here stays the same. But I'm going to break this term up into two. Okay, like so. That's not a big change yet, but now I'm going to break up this whole sum into two parts. Oh. Okay. But actually, this part here simplifies even more because I can pull the t out, and then that t is just multiplying the total income. Okay. When I write it like this, you can start to see that this has kind of the structure of a cost-benefit problem, right? Where this first summation here, you can think of that as the beneficial aspect of the tax rate. And this part over here is the cost part, okay? And here the cost of the tax rate, it doesn't really, it's kind of funny to talk about the cost of the tax rate because it's not as though you're paying money for the tax rate. It's not like you're paying money for labor or something, but it still is a cost. It's just a cost measured in terms of this individual consumption of the private good, of the private consumption. So it's really an opportunity cost. But, that's fine. We can still think of it in this way. We can separate out the objective function into two components, a benefit and a cost. Okay, and once we have that, then we can apply our first order approach. Okay, so the first order condition is what? Well, the derivative of the of the benefit function, oh, I should say I can actually simplify that a little bit more. Let's do it a little bit more. So if you look at it, all right, let's just break it up like so. Break it up even more. Into 3 summations here. But this here is constant. It doesn't depend on I. And so it's just, we're just adding that term n times. And so that ends up just being n times ti beta. This here is just the total income. And there we go. Okay, so again, this is like our benefit, this is like our cost. Okay, now the first order condition is the derivative of the benefit function is equal to the derivative of the cost. So the benefit function, we're differentiating with respect to t, the tax rate. Notice that it's inside this power function term here. All right, so we're going to have to use the chain rule. So if we take the derivative of that thing, we pull the beta down, subtract 1 from the exponent, and now we have to multiply by this coefficient. This here is just a constant, and the marginal cost is just total income. So we can divide by the I. In fact, we can divide by I. Well, let's just do that, fine. And then we'll divide by beta n. And what we get is t times total income, beta minus 1 is equal to 1 over beta n. Well, we can raise both sides to the power 1 over beta minus 1. Beta is actually it's a number between 0 and 1, so to make that, I kind of like to have the exponents positive, so let's write that as beta n to the 1 over 1 minus beta, okay? So solving this, we just divide both sides by I, the total income, and we get this expression. This is the unique solution to the first order condition. I have to say, though, it's not necessarily the optimal tax rate, because this expression that we just wrote down, this could be bigger than 1. It's going to be positive, but it could be bigger than 1. And so we have to be a little bit careful here. And so the optimal tax rate is T star. It's going to, actually, let me write it like this. T star will be equal to this expression that we just solved for if it's less than 1. Or less than or equal to 1. And if that's greater than 1, well, then the optimal tax rate is just 1. And it's actually possible in this model because the way we're measuring the benefit of each member of this group, it has this additively separable form, and it might actually be that the best thing for this group is just for everyone to chip everything in to to this project or whatever it is. So so that's the solution. It's again, it shows that these techniques are maybe more general than you would think at first. And it shows that different applications can use different structure, and the answers can depend on that structure in kind of subtle ways. For example, here we have the possibility of t being bigger than 1, but we have to rule that out, which gives us a solution that has this kind of two-part structure to it. Anyway, so that's enough on the first order approach. Took longer than I expected. So what I want to do next is take a step back. Notice that the way we've set things up, it's actually possible that the maximized net benefit is less than 0, okay? There's nothing that we've assumed so far that rules this out. Like this, and a cost function that looks like this. For example, the log functional form of the benefit function would look something like that. And everything we said before is true. So there is an optimal scale there, and it's unique, and it's positive. It's characterized by the first order condition, which is, graphically it means that the slopes of the benefit and cost function are the same, right? The marginal benefit's equal to marginal cost. So here is our optimal scale. But at that optimal scale, the benefit is less than the cost, and so that means the maximized net benefit is negative. Okay, so another way that could happen, obviously here I did sort of a log functional form for the benefit function, but the cost function could look like this. Benefit function like that. That's not a very good looking picture, but okay. Again, there is an optimal scale. And again, in this picture, the maximized net benefit is negative. So we haven't ruled that sort of thing out, and it's actually irrelevant. I mean, given that the decision maker has to choose a scale, you do the best you can, and if the best gives you negative net benefit, it's still better than it could be, right? It could be even worse. This scale here would be even worse. So X star is still optimal. But in some situations, the decision maker has a choice as to whether they want to even start this problem to begin with, okay? So if you are, if you're a firm, if the decision maker is a firm, you could have a situation like this arise. if you want to enter a market, you know, it could be that the best you can do is make a negative profit. In this case here, what's driving this is that the cost, even in this picture I just drew here, because the cost function has a positive vertical intercept, that means that that even if the firm chooses 0 scale, there's a positive cost. That's called fixed cost. And what it reflects is that to even start production, before you can actually produce the first unit, there are investments that have to be made, training, building a factory, right? So even before the first unit of production, there are costs involved. That's what this vertical intercept reflects. But if you're talking about a firm, well, they have the choice, do you even want to enter that market? Okay, so the way you would think about that from a rational choice perspective is the firm would say, well, if I do enter the market, here's my optimal scale, or in this case, optimal output. I can see that my net benefit of that, or profits, are negative because of this fixed cost. So you wouldn't even go into the market, okay? You wouldn't enter the market. So a different example, if you want to think about a government agency thinking about offering a new service, you might have, it might generate some benefits to citizens, but there could be positive setup costs, just going through the hiring process, having a building, maybe, buying equipment that's needed. You can, it might be that the net benefits that are generated by that service don't outweigh those fixed costs. And so you just don't offer that service. Anyway, so there are applications where the decision maker can decide whether to enter into this problem at all. Right? So we're basically giving them an outside option. You can go ahead and invest, choose your optimal scale, but you have the option of just not entering and having, 0 net benefit. Right? So the way you would solve this kind of problem is basically just a 2-step solution. Step 1, first assume that you're going ahead and entering the market, or you're going to solve this problem. Right? Solve that for the optimal scale. Okay, that gives you the best you can do if you undertake this activity. But you have to check the sign of that maximize net benefit, right? Your maximized net benefit is just evaluating the benefit and cost at this optimal scale. All right. If that sign is negative, so the maximized net benefit is negative, then then you either don't enter the market, or you don't engage in the activity. that is, you opt out. Okay. On the other hand, if it's positive, if the maximized net benefit's positive, then you would opt in, okay, and engage in the activity. There's a question about what happens if the maximized net benefit is 0. Then the decision maker would be indifferent between entering or not. It doesn't really, from our perspective, it doesn't matter which choice the decision maker makes in that case. Okay, so so that's how you would handle this problem, in particular the problem of fixed cost. Okay, it doesn't always have to be an issue, because you can have fixed costs, but a situation like this here, you would enter. Okay, but what we're concerned about is cases like this, where you would you don't enter, you opt out. Okay, so that's the way to handle this. It's actually pretty straightforward. Once you have the tools to solve the optimization problem, you basically just look at the optimized net benefit. If it's positive, you opt in. If it's negative, you opt out. Okay, that's enough for now on this. I'll say a little bit more in the next installment about this kind of two-step solution. I want to focus a little bit more on the firm, and then we will also talk about a multi-dimensional version of the cost-benefit problem. And so that's what's coming up. I'll see you in the next one.